Hi and welcome to this tutorial on HMBC NMR spectroscopy. So the spectroscopy we looked at previously has been something along the lines of this, where we've got a depth edited HSQC, and the depth edited HSQC is relied solely on there being a proton attached to a carbon, so it's a single bond correlation. If there's no carbon attached, for example, if we look here at the carbonyls, there's no proton attached to these carbons, then you won't actually see any signal in the 2D spectrum. So what we're trying to do today with the HMBC NMR spectroscopy tutorial is look at long-range couplings. So these have been multiple bond correlations between a proton and another carbon, and you'll see that this is really useful for assigning carbonyls, and also connectivities between things like this, where you've got spin system. You've got one spin system here, so this represents a spin system here where all the resonances, if you look to the toxy of this, for example, you see that coupling. This proton here would couple to this proton here and couple to this proton here, but then it'd stop because that's the end of the spin system. Well, what HMBC is very useful for, together with NOESY actually and ROSY spectroscopy, is it can actually tell you the connectivity between these spin systems, and we'll use that as well in this tutorial. So let's just delete them a second. Okay, so HMBC is heteronuclear multiple bond correlation. So we're looking at a proton signal. HSQC, which is shown at the moment, would just look at that single bond correlation, so that proton attached to that carbon. HMBC is a bit more special. It can look at multiple bonds, so you got one bond there. Let's do this in red. So that's bond 1, that's bond 2, and if we do this one here, we'll end it at 4, but we've got that's 3 and that's 4. Okay, you can actually look at this proton connected to this carbon. Now also remember, we're looking at carbon 13, so you will see you'll never see a signal for carbon 12, but you'll only see it for carbon 13. It doesn't mean you have to have 4 carbon 13s in a line, it just means that one there has to be carbon 13 if you're going to see it. Okay, so that's multiple bond correlation, and as you can see here, if we looked in this example, we just put that proton back in, and I'll do it in green this time. You've got one bond there, 2 bonds there, that carbon to that carbon, 3 bonds there, and that's your 4th bond. So you wouldn't actually see anything over here beyond that. But if you look at this one here, let's do this in light blue. This one's got a bond there, it's a 1 carbon bond, then it's got another bond there, from the carbon to the nitrogen. It's got another bond there from that nitrogen to that carbon. Now the beauty as well about HMBC is that these correlations can actually go through heteroatoms. So if you're new to HMBC and you see a coupling where you think the spin system will stop, then that's perfectly allowed. You can actually go through these heteroatoms. So this proton could potentially see this carbon here. This one here. Okay? Just undo that. So that's the beauty of HMBC. So let's have a look at the spectrum. So just get rid of this. Yeah. Actually, let's just leave that up. I'll just shrink it down a little bit, just as a reminder. Okay. So this is a HSQC. This is a single bond correlation. Now in a HMBC you will see these single bond correlations, so it's always useful to do a depth edited HSQC or a normal HSQC if you want to. So let's just turn that off and let's have a look what it'll look like with HMBC with single bond correlation with no J-pass filter. This is just the single bonds. What you'd actually see, unlike here, this where you've got this nice HSQC signal, you'd actually see splitting because the proton would couple to a carbon 13. Carbon 13's got a spin of a half, so you'd actually see splitting of these signals. Now this can be a bit of a problem when you're looking at complex structures like this, but it can also be very useful because that tells you the first bond, that tells you what that proton is connected to directly. So that's the first single bond. So if you ever see splitting of the peaks, so they don't quite line up with the, if I just draw a line here in red, so if they don't quite line up, for example this proton here comes from this signal here, but if you look, if I just get rid of the HSQC, you can see now it's split into two there. And this coupling constant here will be the coupling constant for that proton-carbon coupling, and it's roughly about 120, 140 Hertz. So let's say 140. Okay, they do vary. I'm just making this up really, but they're in that region. I've chose that for a particular reason actually, and I'll tell you about that in a second. Okay, so you get some splitting like that, and that can be complicated, but this is HMBC as well. And HMBC, we actually want to look at these multiple bond couplings as well. So let's just get rid of these lines and let's actually put the HMBC spectrum up that we would expect to see. Okay, so the HMBC spectrum that I'd expect to see, if we take out the single bond correlations, would be something like that. Now what I've done here as well, even though it looks quite complicated at the moment, but I'll explain how to interpret it in a second. What I've done, I've actually took out the single bond correlation because you can apply what's called a low pass J filter. Now the low pass J filter is usually built into the parameter set when you run this experiment, but there will be a parameter, usually called constant 2 or something like that. If you look in the, you actually look in the pulse program, and you'll see something like that. Now this might vary. This is more like a Brucker terminology, but if you're operating different machines, you might see different parameters for that. Have a look for something that can vary, and that will be the single bond coupling constant. Now if you go below that, so if you set it at say 140 Hertz, which is usually around the default setting for this value, then anything below that will be seen, anything above that won't be seen. So if you lower this value a little bit, you apply a filter so these couplings aren't seen. And the reason for that is because the single bond coupling constant is actually quite large. The second bond coupling constant is a lot lower, and third bond a bit lower, and fourth bond even lower. And I'll put a list of values up at the side for what these coupling constants are, and they'll be available in the worksheet as well. Okay, so this is important because you can change this value as you run the spectrum, and it will actually filter out this single bond correlation and clean the spectrum up a bit. Now the reason they leave it in and don't get rid of it is because actually, if I just draw this double in here, they can actually be really useful for identifying that single bond correlated signal, and that really means you don't need to do a HSQC if you don't want to. You can just go and see and do the HMBC directly. Okay, so that's a low pass J filter, which is quite useful, and it's something you need to be aware of when you run these NMR spectra. Okay, so let's have a look at the HMBC spectrum here. Now if you look on the spectrum, I've actually grayed out some of these signals here, some of these cross peaks. I don't know if you can see it very well, and you might have to go to HD on the video to have a look at this. But they're a bit greyer than the other peaks there. And that's because they represent the 4 bond coupling. So we're looking at these kind of signals here, so from this proton here all the way over to this carbon here. And they get weaker, so you're looking at coupling constants of about 1 Hertz or possibly lower than 1 Hertz. Now there's a value, if you want to detect that, just like the COSY where we had the mixing time we can change. If you look at the parameter set for HMBC, you'll see a value called delta. Now if you change this, it normally is around about 60 to 80 milliseconds. But if you change that, so that's normally about, let me just write that down, 60 to 80 milliseconds. And that's just the preparation time to let the couplings evolve. If you change that value to about 150 to 200 milliseconds, you will actually see this long range coupling as well. But the downside of that is that the signals will become quite noisy and things like that, and it'll take a lot of time to acquire the spectrum. And also you get some artifacts creeping in from the signal generation, if you will. Okay, so apply that with a bit of caution. And also, if you want to look at these 4 bond couplings, or even the higher order couplings, just bear in mind as well the structure of the compound, because that plays a key role. You're looking at the torsion angle as well, so if you look at the carbon, carbon and carbon there. Now you look at the torsion angle, just like the Karplus relationship, it plays a key role in actually the coupling constant. So you might actually be doing all this for nothing, and you might not see it, basically because of the connectivity and the actual angle between the initial proton and the carbon you're interested in. So that's something to bear in mind as well, and something you need to think about when you're actually interpreting these spectra is actually the structure of the compound and how that will influence the signals you see. So not seeing a signal doesn't mean it's not connected to that carbon in some way, it just means possibly the structure is slightly wrong. So it's not a fault of the experiment, it's just nature really, it's just the way things are. Okay, I'll put those values up at the side, and also I'll put a list of the coupling constants in a worksheet as well on Epistemio. So let's get cracking. Let's have a look at the HMBC spectrum, and I'm going to break it down into the amino acids. That's why I've put this alanine there at the side. So we've just looked at alanine, the signals from alanine. We know we've got a proton, remember it's a proton observed technique, so we've got a proton there, the alpha proton. We've also got protons in the methyl group there, and I'm not going to worry at all about the NHs. So we're just going to look at the ones that are connected to carbon for now. So we look at the alpha proton. If we look at the HSQC very quickly and bring that up, we can see the single bond connections. If we change that low pass J filter as well, we'll be able to see splitting of that, but let's ignore that for now. Let's just have a pure HMBC, if you will. But we'll bounce backwards and forwards to the HSQC just so we can see which one's the actual single bond coupling. So let's turn that off. So this is this one, so let's just circle that just for this part of the tutorial. Okay, so that's our single bond. That's the HC alpha carbon. Okay, so the next one that we see is coupling here. Now we've got the way we're going to read it, if I just get a box, let's see if I can do this, is we're going to isolate it as a box like that, and let's see if I can shade that a little bit. That's a bit too much. Okay, that works. Okay, so we're going to have a look at this box here. Now, this is all to do with the alpha proton. So the alpha proton is connected to something there, and if we have a look across, if we've identified this previously anyway, we'll see that this is the CH3 of the alanine there. And if we go down, we actually see another coupling here, and that's for a carbonyl. And if we look at our structure, I'll just draw this in, I'll look at this structure, we've got a carbonyl here, okay, this one here. So we're actually now able to detect a quaternary carbon in a proton observed spectrum like the HMBC. And we can now identify that carbon there. If I draw a line, if I get this right, it's not necessarily that one. So just move that down. It turns out to be that bottom one there. Okay, so that carbonyl there can now be identified as the carbonyl in the alanine subunit. So for the first time we've been able to actually characterize a carbonyl group. Now let's have a look at the rest of it. There's nothing else there. Let's move on. Let's move the box across. Now let's have a look at this part of the spectrum. If we look at this methyl group here, it's got a single bond correlation. We knew that was this one anyway. So let's move on. We now see this alpha carbon. Well, that's kind of what we expected anyway. We expect it to have a 2-bond correlation with that carbon there of the alpha carbon. And again, we see this carbonyl. So we've got, if we look at the methyl, we've got 1, 2, 3 bond correlation with that carbonyl. And if we had a look at the alpha proton, just draw that in red, that would have been 1, 2 bond correlation with that carbonyl. So you will see them. So the coupling constants there are high enough to see. So that's alanine. So let's just tidy this up, but I'll try and leave that box there actually, because it might come in useful. And I'll keep that line as well actually. Okay, so that's alanine, and we've identified each carbon on the alanine from that. Let's move on to the next part of the spectrum, which is valine. Now valine is a little bit more complex because there's more carbons present. Now we know that this carbon here is to do with the CH3s of the isopropyl. So let's have a look, let's go a bit further on from that. Well, first thing you note, if I just move this, because that shading's a bit confusing, I've put the grey in there for this carbonyl. Now I doubt very much you'll see that unless you really change that delta value, because if you look at the coupling here, if I just draw one of the protons in, change that to a 2, and just draw this in red. So we've got a single bond there, hydrogen to carbon, then you've got another one, carbon to carbon, third bond is carbon to alpha carbon, and then you've got 4 bond correlation from that proton to the carbonyl carbon. So I doubt very much you'll actually see that in a real HMBC spectrum, but I've put it in there just in case you do set that value. Okay, so that's why that one's shaded. But what you can see if you look around, and if we just get the HSQC up again so we can see the single bond correlations, you'll see the isopropyl signal and you'll see the alpha proton there. So let's just get rid of that a second. So this is the alpha proton that we're seeing. Now we know the alpha proton for valine actually comes here. So we're seeing the alpha proton carbon, and we're seeing the isopropyl carbon there, which we know comes here in the HSQC. So we're seeing all the carbon connectivity for that 1, 2 and 3 bond correlation. So we would be able to identify that carbonyl if the signal was strong enough. So we now move on to the other part of the structure where the signal will be a bit stronger. So let me just get rid of those circles. Let's have a look at the isopropyl proton. Well, the isopropyl proton, as we know, comes at this signal, and if we did that low pass J filter, we'll be able to see that as a doublet. We know it's connected to this CH3, there's 2 CH3s there, so we'll see the signal there. If we look, we also see the alpha proton as expected, because that's only 2 bond correlation now. Remember, the hydrogen's coming up there like that, so we've got 1 bond for the hydrogen to carbon, and then another bond from the carbon to the carbon, which is the alpha carbon. So there's 2 bond correlation there. If we then look a bit further on, we've got a 3 bond correlation, and that's from the isopropyl proton to the carbon, to the alpha carbon, and then to the carbonyl. So this one is only a 3 bond correlation, and I'll put it as a 3J there, and you should see that. So for the first time again, from the isopropyl proton, you're able to identify the carbonyl, which is fantastic. So let's look at that, and you'll see the carbonyl for that one, if I just move that up a little bit, is this carbon here. So we've identified the alanine as being the bottom one in the way it's drawn, and the top one there, top carbonyl, is the valine carbon. Now if you look, there's a bit of grey there for the alanine carbon, actually. That's the bottom one, and that's because if you count the correlation there, the bond correlation, you've got proton there to the carbon is 1 bond, then to the alpha carbons are 2 bonds, and now you go from that alpha carbon to the nitrogen, that's 1 bond, and you can go through heteroatoms and you should be able to see that as a 4 bond correlation. Now, like I said previously, that would be weak, so I've grayed that out because you might not see that. But if we go on to the alpha carbon here, and let's just clean this up because it is getting a bit messy. Just get rid of that a second. We look at the alpha carbon, alpha proton, sorry. So we look at the alpha proton, you've got single bond correlation to the alpha carbon, that's the first one. Then you've got second bond correlation to the nitrogen of the valine, and you've got a 3-bond correlation to the carbonyl of the alanine. So this is a breakthrough here because we're actually seeing a quite strong correlation, so we should see that signal for the alanine. So we'll be able to confirm that this valine is now connected to this alanine because we've got a nitrogen carbonyl coupling. So that amide coupling is seen. So the two things to note here. First of all, you can identify the quaternary carbon using this technique, and secondly, you can go through a heteroatom to actually get a through bond correlation, and by doing that we are now able to identify that that valine is connected to that alanine subunit there. So you've got your first connectivity in the series. Just like we used a NOESY to identify connectivities, we can actually use HMBC very efficiently to and powerfully to actually define the connectivities as well. So that's really useful, and that's what I use it for quite a lot. Okay, so that's we've just got the NH proton actually. We're going to say that's it, but we've got the NH proton, so we have a look at the NH proton and we'll be able to get the carbonyl quite strong. It's just a 2-bond correlation to that carbonyl, so that if you can see that, that's really good. You're just going to show that up. And also you're now able to detect carbons from a proton that's not connected to a carbon, so that's incredibly useful as well. Now if we look for the rest of it, you'll see that again I've graded out, so all these 4 bond correlations, that's the proton there to the isopropyl proton carbon, you will not be able to see very well. So I would personally ignore the grayed out ones, but I've left them in there just in case you want to play around with your settings. So in the last amino acid is proline. Let's move that, get rid of that a second. Move that out of the way a second. Okay, so proline's this structure here, and if we look at the alpha proton, I always tend to start at the alpha protons. We've got single bond correlation to the alpha carbon, which we should see, and which you can identify again by the HSQC. So if I draw that, the HSQC would show it as being that one. In fact, I'll just circle all the single bond correlations and then just switch that off. Okay, so we have the alpha carbons there, and then we've got some couplings of the alpha carbon to these CH2s here, which you can see these are nice strong couplings, single and 3-bond couplings to this and this carbon here. And also if we look at the carbonyl, we can identify the ester there from that amino acid as being this one in the middle. Now we could have assigned that as the default one if we wanted to, but I always like to confirm it anyway just to back up everything I'm doing. Now also we can see, very important, the most important bit really, is that we've got a 1-bond, a 2-bond and a 3-bond correlation from that alpha proton to that carbonyl, and that, if you look here, is this one here, which if I get the line will confirm that that alpha proton has some connectivity to that carbonyl of valine. So again, we've identified connectivity of one amino acid with another amino acid there. And similarly, if we have a look at this proton here, we can see that that's got a correlation as well, and that's for this proton here. Okay, so that's basically it for interpreting HMBC spectra. I just want to leave it quickly, just get rid of these a second, just give you some quick tips on how to actually go about interpreting the spectrum. Get rid of that. So as you can see, what I did was I grouped the protons into a line, into a column like that, and just read off the carbons that that proton was connected to. Another technique, see if I can do this, spin it 90 degrees. Another technique, it's not quite 90 degrees, that is to look at the carbonyls there and read them off, and then you can see which carbonyls are actually connected to which protons, and that'll actually help you identify which carbons are which. Now if you looked at the total spectrum, I'll just turn that off, you'll see that it's actually a bit more complicated than meets the eye. And also, if you actually did a HMBC, the resolution of the carbonyls is not that great. Okay, so you'll be seeing, if I draw this in really, you'll probably be seeing, if I draw this in red, these carbonyls here would be all overlapping like this. Okay, you'd have really poor resolution. You might not even see them ones. Okay, so it'd look a bit like that. There'd be a bit of guesswork, and the only way to get around that actually is to reset the resolution around that region. Now it doesn't mean you have a resolution that's poor there and good there. What you do, you just rerun the spectrum. We'll just focus on this bit here. We'll watch out for some aliasing back in, so you have to be aware of that for the carbonyl region. So you reset your resolution to a higher resolution for this region here. Okay, so that's pretty much it for the HMBC tutorial. Just remember, just do these vertical lines and read it off horizontally. So you're looking at 90 degrees. So you apply one line down, like so, and then just read it off as a line going across at 90 degrees. And stuff like that, and just keep moving up and down to read it off. So that one's that one, that one's that one, and so on. And similarly, if you're just interested in the carbonyls, what the carbonyls are connected to, you can actually read it off horizontally first, and then find out that way what that carbonyl is connected to, and so on and so on. So I'll put worksheets up on Epistemio. I'll put a copy of this tutorial up on Epistemio as well. I'll put the coupling constants for the 1, 2 and 3 bond and even 4 bond correlations up there as well. And if there's any more tutorials you'd like on NMR, I'm going to do a few theoretical ones, then feel free to just put it in the comments below. So that's it for now. Bye for now.